Hello and welcome to lecture 5 of computational complexity. So far we have seen the classes P and NP, and we have seen the language set, right? So today we are going to so the next important concept that we will see in this course is that of NP-completeness. So on the way to NP-completeness, we first need to understand what is a polynomial time reduction, right? So what is a polynomial time reduction? Okay, so first of all, a polynomial time computable function is a function that can be computed by a deterministic polynomial time Turing machine, right? So this is a formal definition that is written here. F sigma from any alphabet to any other alphabet or the same alphabet is a polynomial time computable function if there is a Turing machine that let's say given x computes f of x and writes f of x on the tape and stops. Okay, so here it's written w and then writes f of w on the tape and halts. So it's a Turing machine that does not decide but rather computes a function. So given w, it will compute f of w, and we say f of w, f is a polynomial time computable function if there is a deterministic Turing machine that runs in polynomial time that is capable of computing f. And a language A is polynomial time reducible to language B, okay, and it has this notation A less than or equal to B with subscript P if there is a polynomial time computable function. So this part is important, a polynomial time computable function f such that for all w, right, in the alphabet, if w is in A, f of w is in B. Okay, if w is in A, f of w is in B. So just to illustrate that, so there are two requirements here. First is that there should be a polynomial time computable function f such that, so f should be polynomial time computable, that's requirement number 1. 2 is that every w in A should be mapped to f of w in B, and it's if and only if. This means that everything that is not in A should also be mapped to not in B, right? So this is an if and only if. It means that, so just to illustrate, so everything, suppose this is A, maybe this is sigma star, let's say this half is A and this half is A complement, and let's say this is B and this is B complement. So everything over here in the top half should be mapped to the top half, right, and everything in the bottom half should be mapped to the bottom half by f, right? So this is what these are the two conditions of the polynomial time reduction. So the point is that this if and only if condition means that if w is in A, f of w should be in B, right, which is here. And if f of w is in B, that should necessarily imply that w is in A, right? So which is the reverse direction, which also means that something in A complement cannot be mapped to B, because if something in A complement maps to B, then that means the reverse implication does not hold good. So this is another way to think about it. Everything in A should go to B and everything in A complement should go to B complement, right? And so the two requirements again, one is that f should be polynomial time computable, and 2 is that everything in A should be mapped to B and everything not in A should be mapped to not in B, which is written like this: w in A if and only if f of w is in B. So this line over here and this figure over here mean the same thing, right? And further, if A is reducible to B in polynomial time, we say that the function that reduces A to B is called the polynomial time reduction from A to B. Okay, so what is the point of this? What is the point of doing a reduction, or what is the point of doing a polynomial time reduction, right? The point is, this is another way to decide A. Okay, so one way to decide A is to you take A and transform it to B, transform A to B, and then you decide B. So you first so you are given a W and you have to decide whether W is in A or not, but you don't seem to know a way to decide whether W is in A or not. Okay, so you don't know whether W is in A or A complement, right? So what you can do is, let's say you are given a W, let's say for instance W is in A, but you don't know that, and you transform it, you compute f of W. So we know that f of f is polynomial time computable, so it will be taken to something in B, right? And now suppose you know a way to decide whether some given string is in B, right? Some given y is in B. And now we can do that. That decision algorithm can be applied to the f of W that we computed, right? So you can use the B's decision algorithm for B. You run it on f of W and use that to decide A. So this is the goal, or this is one of the goals for doing reduction. So from this, what we infer is that if there is a way to reduce A to B, right, the solving A or deciding A is not too much harder than deciding B, right, because you can convert A to B and then decide B. So the difficulty level of deciding A is not that much higher compared to the difficulty level of deciding B, and that also kind of explains this notation A less than or equal to B, right, which means that, so the way one should think about it is that we are reducing A to B, so which means, let's say B is not that hard, let's say B is rather easy, then A is also not that hard, because you can always transform A to B and then solve B, right. So this is the and the subscript P is to denote that the reduction used is a polynomial time reduction. So we will also see other reductions. You may have seen in theory of computation, you may have seen mapping reductions, where we had, you may have seen a subscript of M. In the future we will see log space reductions, where with another subscript, right. So where the principle is the same, but the constraint on the reduction machine will be different, right. So here it is polynomial time, there it will be something else. Okay, and so we will soon see that if you can reduce A to B in polynomial time, and B itself is decidable in polynomial time, then A is also decidable in polynomial time. Okay, and it is important. So you may ask, why do you restrict the reduction to be a polynomial time computable function? What is the point of this, right? Should, like, say I compute, I can just transform A to B and then solve B. Like, what is the problem if the transformation is difficult to complete? The point is that then it may be possible to brush like do the bulk of the work in transformation, and that is not very good, because that does not give you an idea of the difficulty level of A, right? So the goal here is to understand the difficulty level of different problems and compare it with each other. So if you are not really, if you give the reduction operation too much power, what may end up happening is that you may not get meaningful relationships between the problems. So that's why it's important to limit the power of the reductions, right? So for instance, we saw SAT. Okay, we have not said this already, but SAT is a problem that we know. It's a problem in NP. We saw that in the previous lecture. However, we don't know a polynomial time algorithm for SAT. So which means we don't know of an efficient polynomial. So when I say polynomial time, I mean the deterministic polynomial time. So there is no efficient deterministic solution for SAT as of now. However, it is in NP. So it is one of the problems that could be right. That is in P. That is in NP, but not known to be in P. And it is widely believed that it is not in P, right? So as I said, P versus NP, this is one of the problems. People think it's P is not equal to NP, and P is not equal to NP, and SAT is one of the problems that is in NP, but that is not known to be in P. Okay, so this problem, Now I will show you a way to if you don't limit the power of the reduction, we can solve this problem if you don't limit the power of the reduction. So what you can do is, let's say the reduction can use more time than polynomial time, deterministic polynomial time, right? Let's say the reduction can use deterministic exponential time. So one thing I can do is to, given a Boolean formula, I can try out all the, so let's say there are n variables, x1, x2, etc. up to xn, right? I could, right, so given a Boolean formula phi, let's say it has n variables x1, x2 up to xn, I could try out all possible assignments. So there are 2 power n possible assignments for this, right? So let's say there are 2 power n possible assignments. I could try them all out, right, and check each one of them whether it leads to a true, it evaluates phi to true, right? So this is something I can do, and then one, so basically I am deciding whether phi is satisfiable or not, and then I evaluate f to be 1 if phi has a satisfying assignment, and 0 if phi does not. Okay. So now this process is not in polynomial time because I am trying out all the possible 2 power n assignments. But I have a reduction at the end of it. I have a reduction. So there is a set of satisfiable Boolean formulas and there is a set of not satisfiable Boolean formulas. So all the satisfiable Boolean formulas, so now I have a set of 2 elements, 1 here and 0 here. Now all the satisfiable formulas are mapped to 1 and all the unsatisfiable ones are mapped to 0, right? So now this is something that is easily decidable. You have, basically I am saying, I am giving you a string, you check whether it is 1 or 0, right? It's a trivial thing to check. So this, the mapped solution is something that is easy to check, but so we are reducing SAT to a easy problem, easy language. However, the reduction process is time consuming. So now SAT is considered to be a difficult problem, but we have reduced it to a seemingly simple problem, or we have reduced it to a simple problem. But this reduction is not really meaningful because the reduction has too much power. So for us to get a better understanding or better comparison across problems, it is important to limit the power of reductions. Okay. So that is the point of imposing restrictions on the power of reduction, right? So now this is something that I already mentioned, but I will just quickly go through the details. If A is reducible to B in polynomial time and B is decidable in polynomial time, right? B has a deterministic polynomial time algorithm, then it follows that A also has a deterministic polynomial time algorithm. Why? So it's already what I outlined. Given a W, which we have to decide whether it's in A or not, right? So you compute, so you know it is reducible to, A is reducible to B, and you know the reduction function. So you, given W, you compute f of W and then run the decider for B, right? This is what it is. So given W, you compute f of W and run M on f of W, where M is the decider for B, right? So, and you accept W if and only if M accepts f of W. So basically you test whether f of W is in B and use that to decide whether W is in A, right? If W is in A, f of W is in B. If W is not in A, f of W is not in B. This is something that we know because that's a property of the reduction. And so the correctness is just what I said right now. And the other thing that is to be checked is the so the claim here is that A is in P. So now is this process, if you combine this process, does it give a polynomial time algorithm for A, right? So let's see. So the claim is that both these operations, number 1 and number 2, converting W to f of W, computing f of W, and to deciding whether f of W is in B, both of them run in polynomial time. Let us see. Why is that? This is true because let's say W is of length n, okay, and let's say this computing f of W takes polynomial time. So let me say it is n power k1 time algorithm, okay, and the decision, let's say m runs in let me write m power k2 time, okay, where m is the input length. So I am just using a different input length small m here just to differentiate between this n and this m, okay. So the running time of f is order n power k1 and the running time of m is order m power k2, right. So when you run, so what you do is you compute f of w, sorry, this is something, okay, compute f of w. So this takes order n power k1 time and then you run m on f of w, okay. So this complexity of m power k2 is on the length of the input, okay. So the complexity is usually a function of the length of the input, but the length of the input is the length of f of w. So what is the length? So where m is the length of f of w, but what is the length of f of w? The reduction does not tell us what is the length of f of w, right. It only tells us how much time it takes. Well, if it takes 100 steps to write down f of w, then f of w cannot be longer than 100 bits or 100 symbols, right, because writing each symbol takes one time step at least. So since we know that the input length is n and the running time of the reduction machine is n power k1, the maximum length possible of for f of w is order n power k1. It cannot be longer than that, because if it is bigger than that, then you will not be able to write this much down in that much time, in that many number of steps, right. So m is order n power k1. So together how much time is it? It is order n power k1 plus order m power k2, but m itself is order n power k1, so which is order n power k1 whole power k2, so which is order n power k1 k2. So this dominates this, so eventually what remains is this. But anyway, k1 is a constant, k2 is a constant, so together we have a n power constant, which is a polynomial time thing. So the combined algorithm of transformation and then running the decider for b is also a polynomial time algorithm. When I say polynomial time algorithm, I'm always, the baseline is the input length. So it is polynomial in the length of the input instance. So the input instance here is w. So the length of the w is n. So it is polynomial in n because it's n power some constant, right? Even though it's a bigger constant than either one, so it's k1 here and k2 here, so it's k1 k2, which is potentially bigger, right? But it's still a constant. So so what we have seen is that if a reduces to b in polynomial time and b is in p, then a is also in p, okay. And some other results, it's not so difficult to see. I'll just state them. You could think how we get these things. So one is that if a is reducible, so this result was that if a is reducible to b and b is in polynomial time, then a is in polynomial time. So instead, if b was in NP, then we can infer that a is in NP by exactly the same kind of arguments, right. The next point is that if a is not in P and a is reducible to P, right, then B is also not in P. So this is, here notice that we are using the reverse direction to argue. Why is this? Suppose B was in P, right, then we could just use what I stated here. If A is in reducible to B and B is in P, we could use that to infer that A is in P. But by assumption A is not in P, so B also cannot be in P. If B was in P, then this would imply that A was in P. The next thing is that if A is reducible to B and B is reducible to C, then A is reducible to C in polynomial time. This is because you could just compose the two transformations. Whatever function reduces A to B, you could compose that with, so basically you get an instance A, B and C. You reduce from A to B and then reduce from B to C. You can just combine these functions to get a combined function that reduces A to C. And finally, A reduces to B implies that A complement reduces to B complement. Because if you just look at this definition of reduction, right, the same function is used. So just that the roles of A and A complement and the roles of B and B complement interchange with each other. So now we will just say W is in A complement if and only if f of W is in B complement, but that is logically equivalent to saying W is in A if and only if f of W is in B. Hence, if A reduces to B, equivalently we could say A complement reduces to B complement. Sorry. Okay, so we saw what is reduction and we saw some basic understanding of what is a reduction. Now let me just show you one interesting reduction. Okay, so this is theorem 7.32 from Sipser. So again, whatever I have been talking about in the time complexity part so far is there in Introduction to Theory of Computation by Michael Sipser, chapter 7, right, the chapter on time complexity. So the statement here is that 3-SAT is reducible to CLIQUE. So what is 3-SAT? Phi is a 3CNF formula that is satisfiable. CLIQUE is given G and a number K. G is a graph. G is a graph with a K clique. So this is an example over here. This one. So so G comma 4 would be a S instance because there is a 4 clique here, right? The 4 circled vertices form a clique, right? This vertex 1 is connected to vertex 2, vertex 2 is connected to vertex 3, vertex 3 is connected to vertex 4, 4 is connected to 1, and then 1 is connected to 3 and 2 is connected to 4. However, there is no 5 clique here. There is no 5 vertices that are all adjacent to each other. So clique is a set of vertices that are all adjacent to each other, right? Just as an aside, the fact that we are able to draw this graph without the edges crossing each other, right, that itself is an indication that there is no 5 clique. So there is a result not really related to complexity theory. In graph theory, that states that if you have a 5 clique, this is something that you can just try out, not in complexity theory, right? You try connecting all the vertices to each other, right? So like this, right? So like this, so 1 2 3 4, 1 2 3 4. I don't know. So you will not be able to connect everything to everything else. That's the point. So I think this vertex 1 is connected to everything else, vertex 2 is connected to everything else, vertex 4 is connected to everything else, but the edge between 3 and 5 is missing. Anyway, this is an aside, so I'll just erase it. It's something you can try out for fun. So anyway, this is a no instance if you give k equal to 5 and this graph, right? So this may seem like two different problems, right? So one is some Boolean formula and checking whether it is satisfiable, and two is given a graph, is there a certain pattern between the vertices. Interestingly, you can reduce one to other. So that's what we will see now. So 3-SAT means it's a 3CNF formula, which means it's an and of clauses where each clause is an or of 3 literals. So let's say the clauses are A1 or B1 or C1 and A2, B2, C2 and so on, AK, BK, CK. So there are K clauses where each of A1, B1, C1 etc. can be literals. So each A1 could be could be x1 or x1 complement, x2 or x2 complement. Same thing for b1 could be x2 or x2 complement, x1 or x1 complement, and so on, right? Same thing for a1, b1, c1, a2, b2, c2, and so everything. So for instance, one example is consider phi to be the following, right? So we will base our, I'll give you a pictorial depiction of this example also. This example is also there on in CIPSR, right? So consider this 3-set formula where, so there are some repetitions because deliberately or intentionally we have kept the number of variables to 2, because if the number of variables blow up, then the example does not look like look very small, or it gets very messy with too many lines crisscrossing, right? So the formula is x1 or x2 or x2, right? So which is kind of trivial because x2 or x2 is the same as x2 itself, and x1 complement or x2 complement or x2 complement, and x1 complement or x2 or x2, right? Right. So there are 2 variables here, right, and 3 clauses, and we need to show that 3-set reduces to clique. So this is an example 3-set instance, okay, a Boolean formula in the 3CNF form. The goal is to draw a clique instance. So come up with a graph G, right, and a number k such that, so maybe I'll show here, right, this is the goal. Given a formula, there should be a function or a process to convert the formula into a graph and a number k such that the formula should be true or satisfiable if and only if the graph has a k-clique. If the formula has a satisfying assignment, then the graph should have a k-clique, and if the formula does not have a satisfying assignment, then the graph should not have a k-clique. This is the goal. So what is a way in which you can convert a graph, a formula into a graph and a number k, right? Okay, so now we will explain the construction. So first I will explain the construction, then I will explain why the construction is correct, and the fact that the construction is in polynomial time. So remember, for reduction we need 2 things. One is that the function should be polynomial time computable, and 2, the function should satisfy this w is in A if and only if f of w is in B, right? That is the correctness of the reduction. So both we have to show. So in this case it will be easy to see the time taken by the reduction. The correctness of the reduction we will explain after this. Okay, so what I have done here is I have made 3 sets of 3 vertices each, right? So you could see that this set corresponds to the clause 1, x1, x2, x2. The top set corresponds to the clause 2, x1 bar, x2 bar, x2 bar, and the right side set corresponds to the clause 3, x1 bar, x2, x2, right? So basically one vertex for each, one group for each clause, and within one group 3 vertices, one for each literal in the clause. This is the graph. So there are k clauses or m clauses, there will be 3m vertices, okay, 3m vertices will be there. And then now let's talk about edges. So I've already drawn for convenience. The edges are, so within a clause there are no edges. So you will see within C1 there is none, within C2 there is none, and within C3 there are none. There is no edge connecting 2 vertices in the same clause. And across clauses, so across groups, there are edges, but I don't put an edge between a literal and its complement literal. So between x1 and x1 complement there is no edge. So you see, between x1 and x2 complement there is, between x1 and x2 there is, between x2 and x1 complement there is, everything is there. But between x1 and x1 complement there is none. Between C1, from C1 to C2 also, and from C1 to C3 also. And the same thing, between x2 and x2 complement it is not there. But between x2 and x1 complement is there, and between x2 and x1 is also there. So you make 2 vertices adjacent if they are in two different groups, and two, they are not complements of each other. Right? So no edges between vertices of the same clause, right? And two, no edge between xi and its complement for any i. These are the only rules, and you connect everything else. So you can check in this figure, and everything else is connected. So there are 3m vertices, and between 3m vertices maximum you can have 3m squared, or 3m choose 2 edges, right? So the number of edges is some order of m squared edges is there, right? That's the maximum that you can have. So the construction is simple, right? So the construction takes m square time I've written, so it's actually order m square time, because the rules are very straightforward. You could just have some for loop to compute this graph. So given a formula, you can compute this graph. This is a reasonably straightforward procedure, and it is clear that the procedure will be in polynomial time. It's not that difficult to see. If it is not immediately clear to you, just think about it. Okay, so how you will write an algorithm given a formula that constructs this graph. Okay, now let us see why this construction is correct, meaning the main part of the reduction, or in this case the main part of the reduction, that the Boolean formula is satisfiable if and only if the graph has a k-clique. So here, by our choosing the k, instead of k we will have m itself. So the Boolean formula will be satisfiable if and only if this has a m-clique. Let us see why. Okay, so we will have two directions because it's if and only if. So first we will show that if the formula is satisfiable, G has an m-clique, and then we will show the opposite. If the graph has an m-clique, then the formula is satisfiable. So what does it mean to say the formula is satisfiable? It means that there exists an assignment, right, which sets each clause to true, right? There is a way to assign true false to the variable so that each clause is true, because it's an AND of the clauses. And what does it mean to say each clause has to be true? Every clause has at least one true literal, right? So because each clause is an OR of literals, so it has at least one true literal. It could have more, but it has at least one. Now what you do is you choose one true literal. Okay, so some clauses may have more than one, but you choose one true literal from each clause. So till now we are talking about only the formula. We are not at all talking about the graph, right? So now choose one true literal from each clause and look at this in the graph G. So assume there are m clauses and you can choose one true literal from this clause. Okay, so let us take let's say, is this satisfying? Is this Boolean formula satisfiable? I believe yes. If you set x1 to false and x2 to true, right, everything is satisfied, right? x2 is true, x2 is true, here x1 is false. So what is the true literal in each clause? Here x2 is a true literal, so I will use maybe green color. Here x1 is a true literal, x1 complement is a true literal, right, because x1 is false, and here x2 is a true literal. So these three green vertices correspond to true literals. So now these three literals are in three different clauses, and none of them are complements of each other. Why? Because if they are in complements of each other, they cannot be both true, right? So if x2 is true, x2 complement is false, so you cannot pick both of them to be true. So these are the only conditions that we wanted to have edges between them. They should be in different groups, and they should not contain any I such that xi and xi complement is there, right? So in the graph G, these vertices will form an M-clique. Why? Because we started from the assignment and we picked one literal from each clause. So that automatically places the literals in each of these clauses, right? One in each clause. And second, these are the true, literals that were set to true. So if xi was set to true in some clause, xi complement cannot be set to true in another clause. So xi and xi complement cannot appear together. So what we will have is a bunch of true literals in separate clauses and with no conflicts. So all of them will be chosen, and all of them will have edges between each other. So, and because there are M clauses, there will be exactly M vertices in this set, and they will form an M clique, right? So these M nodes form a clique. So the graph has an M clique. So if the formula has a satisfying assignment, then the graph has an M clique. Now we will show the reverse direction. If the graph has an M clique, if the graph has an M clique, then so notice that this graph has no two vertices within the same group are adjacent to each other, right? So you cannot have two vertices in the M clique from the same group or the same clause. So we will have at most one vertex from each clause, right? At most one vertex from each clause. So there are M cliques, so M vertices, and we can have at most one from each clause, right? Which means we should have exactly one from each clause, right? We cannot have more than one, but we have to have M of them. So there has to be exactly one from each, right? And by the rules, we cannot have xi and xi complement both in the clique, because if xi and xi complement were both in the clique, then these two will not be adjacent, so they cannot be part of the clique, right? So for instance, in this figure, in a clique, x1 and x1 complement cannot be both there because these two are not adjacent, right? So this clique that we picked here, x1 complement x2 and x2, they form a clique because they are all in different groups, and they are all not like xi and xi complement, right? So we cannot have both xi and xi complement for any I in the clique, right? So we have M literals, one from each clause, right? So till now we are talking about the graph. The graph has an M clique, which means one vertex, at exactly one vertex comes from each clause. When I say clause, I mean the clause part in the graph. And we know that no two of xi and xi complement or together can come. So that means we have M non-contradicting literals, one from each clause. So now let us look at them in the Boolean formula phi, and we will make all of them true, right? So suppose x1 is there, x2 complement is there, x3 complement is there, and x4 is there. So we will assign true to x1, false to x2, false to x3, and true to x4, and this will certainly create a satisfying assignment for the Boolean formula. Hence each clause will be set to true and the formula will be satisfied. And perhaps maybe the Boolean formula also has a variable x5 which is not set to true or false, but it doesn't matter what we set to that, because just from the set x1, x2, x3, x4, every clause will be set to true. So this way, so now we have shown that if the graph has an m-clique, then the Boolean formula is a satisfying assignment. So we have shown both ways. If the formula is satisfiable if and only if the graph has a m-clique, right? So this is an example of a reduction. So we converted satisfiability to the clique problem. So given an instance of satisfiability, we constructed a graph such that the formula is satisfiable if and only if the graph has a certain clique, certain sized clique, and then we showed that that is indeed the case. And we also showed that the transformation that is used is polynomial time. So this completes the proof that there is a reduction between satisfiability and clique. So again, this shows only one direction. We can reduce satisfiability to clique. This does not show that the other direction holds, right? It is not clear if you give a graph with a clique, this corresponds to a Boolean formula. Not all graphs with cliques has to be in this form. So this is something for you to think about. Excuse me. Just one more small comment before I stop this lecture. I think I'm over time. So we used a certain type of structure to convert satisfiability to clique, right? We use a certain graph, certain type graph. So sometimes this specific type of structures are called gadgets. So gadgets are like, it is just a fancy name for like these structures that are used to transform one problem into another. And we will see more examples of these. And with that, I conclude this lecture 5. So what we have seen is what is a reduction, what is a polynomial time reduction. Two things. One is the time required for the reduction, and the W is in A if and only if f of W is in B. And some consequences of reductions, right? So we saw some results, and the fact that 3-sat is reducible to clique in polynomial time. With that, I end this lecture. Thank you.